I will also import a function train underscore test underscore split from sklearn.model underscore selection. I will import matplotlib. I will also import pandas. I need a panda here. I need display. So I will import display from IPython, and I will also import Seaborn as a SNS. So these are the important libraries which I need for this project. Let's run this cell to import all these necessary libraries. Now here I am getting a data set from a Seaborn. I have already import Seaborn as SNS. So there is a data set named as Iris. So that data set is present in Seaborn. So here I will load dataset from Seaborn. So the command is SNS. SNS is the name of a Seaborn library. So I have imported Seaborn library with the name SNS. SNS dot the function is load underscore dataset. And here I am importing a dataset known as Iris dataset. And after importing, I am saving this dataset into a variable known as Iris. So this dataset is basically a flower dataset. This dataset contains 3 different flowers, and we also have the feature of the flowers. So basically we have to classify 3 different flowers in this project. That's why it is a multi-class project. That is, we have more than 2 classes. Let's run this cell and load this dataset, as well as we want to see the shape of the dataset. So if I run this cell, I get the shape 150 by 5. So I have 150 sample. So what actually is happening, I have 3 different kinds of flower. So I have 50 samples for each flower. Next is that I have 5 columns. So out of 5 columns, the 4 columns belongs to the feature and 5th column belongs to the class or label of the dataset. Here I can see the top 5 samples of a dataset. If I want to see, so these are the top 5 samples out of these 50. So the feature are sepal length, sepal width, petal length, petal width, and these are the species. Here, since I have selected only 5 samples, therefore that is, I am observing the head of the dataset. Therefore, I can only see the first species or first label, which is setosa. So if I can expand it to like 100 features, or I just want to see the complete data set. So we can see that I have 150 samples. We have a setosa, we have a virginica, and between them we have another versicolor, the third kind of a flower. Now it's time to see the species. So species are present here. So if I want to see the species and the 3 different labels, which I said about this dataset, that this is a dataset of a flowers with 3 different kind of flower. So here are the 3 different labels. So the labels are setosa, versicolor, and virginica. Since these 3 are the flowers, so every flower has a sepal length, sepal width, petal length, and petal width. So this is the explanation of the Iris dataset. So Iris dataset is a dataset of flowers having 4 features, and in this dataset we have 3 kinds of flower named as setosa, versicolor, and virginica. Now it's time to see these flower. We can display these flower. So first I am going to show you the Iris setosa, that is the setosa class of this dataset. So I am getting this from this site. So I am using from ipython.display. I am importing the image, and I want to show you the image of this setosa class of a Iris dataset, which I am getting from this website. Let's run this cell and observe. So this is the image of setosa flower. Similarly, I can see versicolor flower. If I run this cell from the same website, I can get the versicolor, and similarly I can get the virginica label of the flower, that is the third kind of flower. So we can see that we have 3 different kind of flowers. Their petals are of different length and shape. That's why we have the features sepal length, sepal width, petal length, and petal width. So till now, what we have done in this project is that we have loaded a data set from Seaborn. This is an Iris data set. This Iris data set is about 3 flowers. So the name of the flowers are setosa, versicolor, and virginica, and we will use these names as a label in our data set. So these are the images of these flowers, setosa, versicolor, and virginica. Now the problem is we have to transform these labels into integers. So the names are Setosa, Versicolor, and Virginica. So we cannot give these names directly to our computer or our machine. We need to transform them into the integer. So look at how I am transforming these labels into the integer. So I am getting iris.species.replace. So the iris.species is the species is the column where these label are present. If we go back, we can confirm species is the column and iris is the name of the data set. So in order to get these, I need iris.species and I am using a function dot replace. So what to replace? So replace Setosa with value equals to 0 and I want to replace it permanently. Therefore, in place is equals to true. Second, I am replacing Versicolor with the value 1 and Virginica with the value 2. So after this transforming, the name of my labels will be 0, 1, 2, where 0 will indicate Setosa, 1 Versicolor, and 2 Virginica. Let's run this cell. And now if I want to see the head of my data, I can see that instead of Setosa, the 0 is written in the labels. Now here iris.species.value counts. If I want to see now, I have 50 samples belongs to class 0. I have 50 sample belongs to class 1 and I have 50 samples belongs to class 2. Now these are the species. Previously the name was Setosa, Versicolor, and Virginica. Now the name of the labels are 0, 1, and 2 and they are present in the column name species in our dataset. So here by using the function dot value counts, we are able to find the number of samples belongs to the particular class. Now it's time to extract the features. Extracting features means I need all these columns except one, except the last column, that is the species. So in that case, I am using iris.integerLog. I need all the rows, I need all the columns except the last. We know that the last column index is -1. So here I am extracting the features which are present in all the columns other than the last column. So let's run this cell to extract the features. And here I am extracting the labels which are present only in the last column. So I am extracting all the rows of the last column and these are called the label of the dataset. So I have extracted features and label. Now it's time to perform a train test split. So for train test split, I am using 20% data as a testing. Therefore, 80% data will be used as a training. So I am passing X and Y values to my train test split. So these are the feature, these are the label. So the test size is 0.2 and the random state is equals to 42. Now let's run the cell to get the train and test split. So the output has 4 values. After performing this function, I will get the training component of the data, the testing component, the training labels, and the testing label. So here, if I want to see the shape of my testing component, so we can see that its shape is 30. The reason is that we have total 150 samples. Out of these 150 samples, we are using 20% as a testing and rest 80%. So our test samples are 30 and every sample has 4 features. So we can see that we have 4 features: sepal length, sepal width, petal length, and petal width. So the size of our testing data after the splitting is 30 by 4. We have 30 sample and 4 feature. Now it's time to standardize both the training and testing part. So for this, we have to import standard scalar, which is present in Scikit-learn.preprocessing. So I will import standard scalar. Here I am instantiating standard scalar and I am assigning the variable sc to it. And now it's time to apply these standardization both to the training and testing component of the data. So we have to be careful. We study in the previous projects that whenever we have to standardize our training component, we have to use fit_transform. Fit function can only be used for the training component. It cannot be used for the testing. So for training, we will use fit_transform. And for testing, we will just transform this into the standard scalar sc.transform. Let's run this cell and we get the standardized data. Now it's time to applying logistic regression. Here I am instantiating logistic regression and I am calling it as a model. Here I am fitting my model to the training component of the data, that is X train and Y train. So basically with this line of code, I am training my model with the training data. And that trained model is called LR. So LR is my trained logistic regression model. Now the next important step is to get the probabilities of classes about the test data. So we have now seen this function many times, which help us to find the probabilities of the classes. So the function is LR. LR is our model. So the function is dot predict underscore prob A. It is giving us the probability of a testing sample with respect to each class. Let's run the cell to see the probabilities. Now there is a change. Previously, whenever we transform our classes into the probabilities, we have two columns. Now we have three columns in these probabilities because we have three class. Class 0, which is Setosa, class 1, which is versicolor, and class 3, class which is Virginica. So we have three classes, but they are represented by 0, 1, and 2 because index in Python start from 0. So this is our 0 class, this is our first class, and this is our second class. So we have total three classes, but they are numbered as 0, 1, and 2. So if we see here, the probability with class 1 is high. If we see the sample one, it has three probabilities. So it has the high probability with class 1. It means our first test sample belongs to class 1. Similarly, if we see our 40th sample, it has the high probability with class 0. So it belongs to class 0 of the data. Let's get the class prediction. So for class prediction, we are using lr.predict. So here we can see that our last sample belongs to class 0 and our first sample belongs to class 1 because it has high probability with class 1. So in this way, we have calculated the probability for the test samples for each class. Now we have also calculated the class predicted, that is the prediction class. Now it's time to create a table where we can see all these probability values and predicted class. So in the previous projects, we know how to create that table. Now this table will have 4 columns because we have 3 classes. So we will have the first column, we will have probability of class 0. For second column, we will have probability of class 1. For the third column, we will have probability of class 3. So for these 3 columns, we will get these 3 values. So this will be the value of the first column in the table. This column will be the value of a second column, and this column will be the value of a third column in the table. And the fourth column has a name predicted class, and this column will get these values. So let's run this cell to see the table clearly. So we can see that our first column represents the probability of first sample with class 0, then with class 1, and the third column represents its probability with class 2, and here is the prediction. So we can confirm that this sample has highest probability with class 1. Since it has a highest probability with class 1, so our model prediction is right. Model is predicting that this sample should belong to class 1. Similarly, we can go through for each of these 30 samples, and we can confirm here that if we see this sample, it has the highest probability of 0.98, that is 98% with class 2. Therefore, our model is assigning class 2 to this sample. So we have seen that our model is generating the correct value of the probabilities as well as the class. So we have formed this table. Now it's time to evaluate the model. Model has given us the values of probabilities, and model has given us the class predictions. Now it's time to evaluate. For evaluating, what I can do is I can calculate the accuracy. Now how to calculate the accuracy here? So basically accuracy is the mean value of ypred is equals to ytest. So basically we have to see how many ypred is equals to ytest. If I run this cell, I can see all ypred are equals to ytest. So this is a great performance of our logistic regression model. We can see that, and we are expecting that we are getting the 100% accuracy because there is no false value. All the predictions made by our model are equal to the true values. So if I calculate the accuracy here, I am getting the equal values, and here I am taking the mean. Means I am summing these values, and then I am dividing with the total number of samples. So if I run this cell, the accuracy will be 100%. So we can see that I have transformed the accuracy into percent by multiplying the accuracy equation by 100. So the accuracy is 100%, and we have confirmed from here that all the predictions made by model are exactly equal to the actual label of a testing component of the data. Now it's time to create a confusion matrix. Here we are setting the weights and font for the confusion matrix. Here I am importing the confusion matrix, F1 score, precision score, recall score, accuracy score, and confusion matrix display. All these function from sklearn.matrix. So we have seen in previous two projects that how to import this using sklearn.matrix. Let's run this cell to import. Here I am creating my confusion matrix. So we can see this is the shape of the confusion matrix with the accuracy of 100%. So if your data accuracy or if the accuracy of your model on the testing component is 100%, so this will be the shape of your confusion matrix. So one more important thing to remember is now we have three labels, 0, 1, and 2. That's why the size of this confusion matrix is 3 by 3. So we can see that all the true values are present in the diagonal, and all these values are basically the error. So here there is no error. So we can see that if the accuracy of a model is 100%, its confusion matrix looks like this. So all the values are in the diagonal, and we know from the theory of the confusion matrix that the diagonal of confusion matrix returns the true values, that is a true classified symbol, and other diagonal values are the errors or they are the false classified value. So there is no false classification in this confusion matrix because the accuracy of our model is 100%. Now it's time to calculate accuracy, precision, recall, and F1 score. We have already imported this from sklearn. Here you can see that we have imported F1 score, precision, and recall score as well. So it's time to calculate accuracy, precision, recall, and F1 score. So here is the typo. I have to adjust it. This is not F, it should be AND. So now it is calculating accuracy, precision, recall, and F1 score. So we have seen these equations now many times before this project, that these equations are used to calculate accuracy, precision, recall, and F1 score. Now it's time to run this cell and see the values. So we can see that every value is 1. That is, accuracy is 100%, precision is 100%, recall is 100%, F1 score is 100%. So we have a clean data, and our model has performed so well on this data that its accuracy, precision, recall, and F1 all values are 100%. Now it's time to get the classification report. So I am importing classification report from sklearn.matrix, and here I am printing my classification report. So we can see that we have 30 testing sample, and we calculate the precision, recall, F1, and accuracy using all these 30. So we can see that the average value for the precision, recall, and F1 score is 1, and the value of the precision, recall, and F1 score for individual class is also 1. Now it's time to plot ROC curve. So we have import ROC curve display from sklearn.matrix. We have seen these lines of code previously in project 2 and project 3 as well. Let's run this cell to see the ROC curve. Now this ROC curve is very interesting. Now I can reduce the size so that I can clearly visualize this. Let's run this cell, and now we can clearly visualize this ROC curve. So we know from our previous projects and theory that ROC curve is the curve between the false positive rate and the true positive rate. And the area under the curve represents the precision of the model. Since in precision calculation, we use the false positive and true positive, therefore area under the ROC curve represent the precision of the model. So this AUC, that is area under the curve, is 1 or 100%. And we can see that there is no false positive value because model has classified every sample correctly. There is no wrong classification, whether it is false positive or false negative. But we do not need any negative label for ROC. So we can see that this has a 0 value, and we can see this true positive has a 1 value, that is 100%. So all the labels are correctly classified. Therefore, the area under the curve here is 100%. That is, the precision of our model is 100%. So in this project, we learn how to implement logistic regression for a multi-class problem. We select the iris dataset, which has 3 classes, that is the setosa, versicolor, and virginica, and we apply logistic regression model. So our logistic regression model has performed well, and we get the value of accuracy equals to 1, that is 100%, and same values for precision, recall, and F1 score. And we also see the important thing here, that if our classes are 3, then the size of confusion matrix is also 3, and the true values are present only along the diagonal of the confusion matrix, and rest values are the error or the misclassification. So we see when the accuracy is 100%, there is no error values and all the classes are classified correctly. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture.